Brazing makes it possible to create strong bonds by directly joining metal atoms from the base material and metal atoms from the brazing alloy. However, many metals have an oxide layer, and the base material and brazing alloy cannot be directly bonded with this oxide layer in place. Bonding can be extremely complex for materials with a strong oxide layer in particular, such as stainless steel. For this reason, chemicals called fluxes are used to remove this oxide layer and fully expose the metal atoms for brazing in open-air atmosphere. However, this method makes the process much more complicated and also requires post-processing, so it is not well suited to mass production. To overcome this limitation, a method is used where the flux is replaced by a reducing gas, such as hydrogen, to remove the base material oxide layer in order to allow for automatic and continuous mass production. Hydrogen is an optimal reducing gas for removing oxide layers, as one of its properties is that it attempts to strongly bond with oxygen to form water, and it also has high thermal conductivity. This continuous hydrogen brazing furnace is a piece of equipment which is used to achieve mass production by utilizing hydrogen and applying heat to remove oxide layers and carry out continuous brazing. Let's take a look at the brazing process using the continuous hydrogen brazing furnace. First, brazing alloy is supplied to the product joint locations. The product is then loaded into the continuous hydrogen brazing furnace mesh conveyor belt in this state. The interior of the continuous hydrogen brazing furnace is filled with hydrogen. A humpback design is used for the structure of the furnace with inclines at the entry and exit ends, which is more effective at preventing the inflow of external atmosphere inside the furnace than straight type of furnaces. This also makes it possible to reduce the amounts of gas used. When a product is heated inside the hydrogen-filled interior, the oxide layer bonds with the hydrogen to form water and evaporates. This results in the exposure of the metal atoms, then the melted brazing alloy moves between the two base materials and permeates them via capillary action. Next, the product passes through the cooling zone, and as the temperature decreases, the brazing alloy hardens and forms a strong bond between the two base materials. The product is cooled to room temperature by the time it exits the furnaces, so it can be safely removed. This is how the continuous hydrogen brazing furnace allows for efficient and continuous brazing to be carried out. Hydrogen has an extremely strong reducing capacity, which allows for stable and high-quality processing of event-based materials with strong oxide layers such as stainless steel. In addition, stable quality can be maintained if the heating times and temperature settings are configured to suit the base materials to be bonded and the required conditions, making this equipment extremely well suited to mass production. A further benefit is that fully heating the materials in this way results in bonding with less deformation compared to partial or localized heating of materials. Furthermore, the equipment can braze multiple locations simultaneously and create superior finishes. This continuous hydrogen brazing furnace thus has the potential to help resolve a variety of issues at manufacturing plants which carry out metal bonding.